Okay, we're talking about chemical reactions. We're going to cover lesson 4. And I'm just going to kind of go through the high points so that you guys have a good idea of what I expect you to know. First of all, it says right here that a chemical reaction is the process in which atoms are rearranged to produce new substances. During a chemical reaction, bonds that hold atoms together may be formed or broken. Those bonds, remember, are the chemical bonds that occur because of electrons being gained or lost or shared. Okay? The next thing is really important. The properties of substances produced in a chemical reaction are different than the properties of the original substances that you started with. Okay? So a change in properties is a sign that a chemical reaction may have happened. And there are several things, several signs, several pieces of evidence that you can look for in order to determine that a chemical reaction has happened. For example, it says, a solid substance called a precipitate may form. A color change may happen. A change in odor. A gas may form. And a temperature change may occur also. And I'm talking about temperature changes that occur without you putting something on the stove or in the freezer or something like that. A temperature change that happens on its own. Okay? All right, we've got a couple of examples of chemical reactions to look at. And when I get back, we will look at a few more. Here, we have a black column forming because someone took sugar, white sugar crystals, and reacted it with concentrated sulfuric acid. Okay? When this occurs, what pieces of evidence do you see for chemical reactions, for a chemical change? First of all, there is a color change. The substance goes from white to black. Okay. There is gas given off. So bubbles up. Also, even though it's hard to tell from the picture, there is an odor change as well. On this one, you have a yellow liquid and a colorless liquid. As soon as they touch each other, they react to form a red precipitate. So, what pieces of evidence do we see in this particular chemical reaction? We see again a color change. And we also see the formation of a precipitate. Now, if you know anything about weather, you might have heard of precipitation. And precipitate or precipitation just literally means something that's falling. So when we talk about weather and we talk about precipitation, we're talking about something that's falling out of the sky, as, you know, like rain, sleet, snow, or hail. In chemistry, when we talk about a precipitate, we're talking about a substance that forms in a solution that's not soluble. And so that substance settles down to the bottom of the test tube. It doesn't stay dissolved. Okay? So precipitation. Okay? Down here, okay. So if you didn't get a chance for this, it's color change and precipitation. All right, what if we take vinegar and react it to with baking soda? This is something that's very common. You notice that we get a lot of gas bubbles forming. And gas bubbles, the formation of gas bubbles is another sign of a chemical reaction. Okay. And then we have this guy obviously smelling that there has been a chemical reaction that occurs in the milk jug, and it now smells bad, so there's an odor change there. And it's possible there may be a slight color change too. Okay? But those are all pieces of evidence for a chemical reaction. So what I want you to do right now is go to your notes area, wherever you have room, and I want you to list those. Okay, so make sure you do that. Okay, so hopefully you had a chance to write down the pieces of evidence, the things that are that we can tell help us, well, things that help us understand that a chemical reaction has occurred. So now we're going to be on page 151, and we're looking at how are chemical reactions modeled. Well, before we can really talk about chemical reactions, we have to understand how to write chemical formulas. And chemical formulas are used to represent compounds. So a chemical formula uses symbols and numbers to represent a substance. Okay, for instance, here is a chemical formula for the compound known as water. It's 2 hydrogens and 1 oxygen. Okay. The numbers that are written below and to the right of the chemical symbols are called subscripts. Okay. And the subscripts tell you how many of that particular element there are. So the subscript on the H is 2. That tells you there's 2 hydrogens. There's actually no subscript written over here for oxygen. That doesn't mean that oxygen has no subscript. It just means that the subscript is understood to be 1 if it's not written. So we have 1 oxygen and 2 hydrogens. Okay. All right, we've talked about how to write chemical formulas, and we've talked about subscripts. But in order to represent an entire chemical reaction, we need to do that with a chemical equation. So a chemical equation is an expression that uses symbols to show the relationship between the starting substances and the substances that are produced by the chemical reaction. Okay, so for instance, down here, we have a chemical equation that has carbon and oxygen reacting to make carbon dioxide. Okay? The substances over here that you begin the reaction with, okay, are your reactants. And that's what you start with. So you begin with reactants. Okay? So these are your reactants. And then what is made in the chemical reaction and what you end up with are products. Okay? So it's similar to a math equation, except for instead of an equal sign, you have a yield sign, which means produces. Okay? So that yield sign, you can sometimes say it's yields, or sometimes they'll say produces. Okay. All right, one of the really big concepts that I want you guys to make sure that you understand is the law of conservation of mass. I'm now on page 152. The law of conservation of mass states that matter is neither created nor destroyed in ordinary physical and chemical changes, meaning that matter is not created or destroyed during normal chemical reactions. Okay? And this law means that a chemical reaction must show the same numbers and kinds of atoms on both sides of the arrow. Okay? Since nothing can be created or destroyed, we have to wind up with the same numbers of elements and the same types of elements that we started with. Okay? And we do this by taking our chemical equations and balancing them, because we have to make sure that we wind up with the same amount of stuff that we started with. Okay? All right. How do you balance an equation? Well, you balance an equation by using coefficients. And a coefficient is the big number that's in front of a chemical formula. So, for example, 3H2O represents 3 water molecules because 3 is the coefficient. Okay? Please understand that only coefficients, never subscripts, can be changed when balancing chemical equations, because if you change a subscript, then what you've done is you've changed the chemical formula and it's no longer the same compound. Okay? And they give you this example. H2O2 is hydrogen peroxide. It's not water. It's got hydrogen and oxygen in it, just like water does. But it's got very different properties from water. So changing the subscripts is a big, big no-no. You cannot do that. So when you balance chemical reactions, you only balance by changing the coefficients. Okay? All right, so it says, what is the difference between a coefficient and a subscript? Well, a coefficient is a number that applies to the entire molecule or the entire compound. But a subscript is a number that only applies to the element that it's written after. Okay, so it does not apply to everything. Okay, all right, so let's look at this sample problem to balance a chemical equation. So we have carbon reacting with oxygen to produce carbon monoxide. Okay, carbon, I have 1 on the reactant side and I have 1 on the product side. But I have 2 atoms of oxygen on the reactant side and only 1 on the product side. So something has happened. If I leave it this way, what I'm saying is that somehow an oxygen has magically disappeared, and that can't happen. So what do we do to fix it? Well, to balance the number of oxygens, we place a coefficient of 2 in front of the carbon monoxide, the CO. And now do you see that they're illustrating an additional CO because there's now 2 of them? Okay. Well, if I have 2 carbons over here now, I also have to have 2 carbons over here. So I go back and put a coefficient of 2 in front of the carbon here. And once I've done that, I am showing that I need 2 atoms of carbon to react with a single molecule of oxygen, because a single molecule contains 2 atoms, to produce 2 molecules of carbon dioxide. Okay, so let's double check and make sure that we have the same number of everything on both sides. I have 2 carbons on the reactant side. I have 2 carbons on the product side. I have 2 atoms of oxygen on the reactant side, and I have 2 atoms of oxygen on the product side. So it is balanced. I have observed the law of conservation of mass. Nothing has been created or destroyed. I have the same amount of mass on the reactant side as I do on the product side. Okay, so this time it's time for us to try it on our own. And the first thing you need to do is count the number of atoms of each element in the reactants and the products in the unbalanced equation. Over here on the reactant side, I have 2 hydrogens, and I have 2 oxygens. But on the product side, I have 2 hydrogens, but only 1 oxygen. Now remember that the rule is I can only add whole molecules. Meaning that I'm going to balance by coefficients, because I can only add whole things. I can't add parts of stuff. So to balance the number of each type of atom, place coefficients in front of the appropriate chemical formulas and sketch the products and reactants, showing the correct number of molecules of each. Okay, so visually, here's our situation. We have a molecule of hydrogen, which is 2 atoms of hydrogen. We've got a molecule of oxygen, which is 2 atoms of oxygen. On the product side, we have 1 molecule of water. I can only add whole molecules. Okay, so I'm going to start with the oxygen. I have 2 over here and only 1 over here. I can't just add oxygen. I have to add a whole entire molecule that contains oxygen. So I have to put another water molecule over here. Well, when I do that, I notice that my oxygens are balanced now. I have 2 on the reactant side and 2 on the product side. But now I notice on the product side, I have 1, 2, 3, 4 hydrogens, and I only have 2 over here. Again, I can only balance by adding whole molecules. So I'm going to go back to the reactant side and add a whole molecule of hydrogen. And once I do that, the law of conservation of mass is observed. Everything is accounted for. So my coefficients, I have to have 2 molecules of hydrogen, 1 molecule of oxygen. And honestly, you wouldn't write that coefficient. You would just leave it, because coefficients of 1 aren't written. And then I have 2 molecules of oxygen. Okay? If I break it down and do it